But to fully understand how Mars works, it's important to get familiar with the key terms that define its structure. What are the fundamental concepts behind this model, and why do they matter? That's what we're exploring next. To truly understand how Mars works, we need to break down the key terms that define its structure. These are the building blocks of the model, the fundamental concepts that make it so adaptable and powerful. Without them, Mars would just be another regression technique, but with them, it becomes a dynamic, nonlinear modeling powerhouse. At the core of Mars are basis functions. These are the small, flexible mathematical components that allow Mars to model nonlinear relationships. Instead of using a single equation to represent the entire data set, Mars breaks it into sections, using different basis functions in each region. These functions capture shifts, interactions, and complex dependencies, allowing the model to adjust dynamically to the data. To structure these basis functions, Mars uses knots. These are the points in the predictor space where the relationship between the predictor and the response variable changes. Think of them as the turning points in the data where a price drop suddenly increases demand or where a change in temperature drastically affects energy consumption. Knots define where new basis functions are introduced, helping Mars capture shifts in trends. Splines are another key concept, providing smooth transitions between different sections of the data. Unlike traditional stepwise regression, where changes happen abruptly, splines create a continuous piecewise function that allows for gradual shifts in the model. This ensures that Mars doesn't just capture patterns, it does so in a way that maintains stability and interpretability. Then there's the forward pass and the backward pass, the two-phase process that makes Mars unique. The forward pass aggressively adds basis functions, capturing as much detail as possible. It doesn't worry about overfitting. Its job is to collect as much information as possible. But that's where the backward pass comes in, pruning unnecessary basis functions to refine the model and ensure it generalizes well to unseen data. These components work together to give Mars its non-parametric flexibility. Unlike traditional regression models that assume a fixed functional form, Mars doesn't impose any structure. It lets the data define the shape of the model. This makes it one of the most powerful tools for handling complex, high-dimensional datasets. Now that we understand the core concepts behind Mars, the next question is, how does the full algorithm come together? How do all these terms interact in the step-by-step modeling process? That's exactly what we're about to explore. Mars isn't just a collection of terms. It's a structured algorithm, a step-by-step process that takes raw data and transforms it into a highly flexible predictive model. It's a two-phase journey, moving from an expansion stage, where the model learns everything it can, to a refinement stage, where it distills that knowledge into its most essential form. This process is what gives Mars its power, allowing it to adapt to nonlinear relationships while maintaining interpretability. The algorithm begins with initialization, where the model starts with nothing but a simple intercept term. This is the baseline prediction, the average response value in the dataset. At this point, Mars has no knowledge of the relationships between variables. It's a blank slate waiting to learn. Next comes the forward pass, where Mars aggressively adds basis functions to improve model accuracy. The algorithm systematically tests different splits in the data, identifying knots where relationships change, and introducing new basis functions at these points. It evaluates all possible interactions, considering whether combining variables improves predictive performance. This brute force approach leads to a model that captures every possible pattern, but also introduces unnecessary complexity, making it prone to overfitting. Once the forward pass is complete, the model moves into the backward pass, where it systematically prunes unnecessary basis functions. Each term is evaluated based on its contribution to model accuracy, and those that add little value are removed. This phase is crucial. Without it, Mars would be an overcomplicated mess, full of noise rather than meaningful relationships. The backward pass ensures that the final model is simpler, more interpretable, and generalizes well to unseen data. Finally, the model undergoes selection, where the optimal set of basis functions is chosen based on criteria like generalized cross-validation, GCV, or adjusted R-squared. This ensures that the final version of the model balances fit and complexity, providing a robust representation of the underlying data patterns. This structured two-phase approach is what makes Mars so powerful. It's not just a model, it's an adaptive learning process that builds itself from the ground up, refining its predictions in a way that traditional regression models simply can't match. But how do you actually apply Mars in practice? What tools and libraries are available for implementing it? That's what we're covering next, the software options for using Mars in real-world projects. Mars isn't just a theoretical concept, it's a practical tool that can be implemented using various software platforms. Whether you're working in Python or R, there are specialized libraries that allow you to build, train, and evaluate Mars models efficiently. Understanding these tools is key to applying Mars in real-world scenarios, whether in finance, healthcare, or marketing. In R, the most widely used package for Mars is Earth. This package provides all the necessary functions to fit Mars models, visualize basis functions, and perform cross-validation to prevent overfitting. It supports both univariate and multivariate response variables, making it an excellent choice for predictive modeling in statistical and machine learning applications. Additionally, the MDA package offers extra functionality, including tools for model selection and diagnostics, further enhancing Mars-based analysis. For Python users, the go-to implementation of Mars is PyEarth. This library is designed to integrate smoothly with the broader Python data science ecosystem, working alongside tools like NumPy, Pandas, and scikit-learn. It allows users to fit Mars models efficiently and provides built-in visualization tools to interpret the fitted splines. While scikit-learn itself doesn't have a native Mars implementation, its suite of regression and model evaluation tools can be used alongside PyEarth to fine-tune and assess Mars models. Both R and Python implementations offer key customization options, including control over the number of basis functions, interaction depth, and pruning criteria. They also support visualization features, allowing users to see how the model splits data, where knots are placed, and how predictor variables interact. Choosing the right tool depends on the context. If you're working within a statistical computing framework, R's Earth package is a robust choice. If you're integrating Mars into a machine learning pipeline, Python's PyEarth provides more flexibility for working alongside other predictive models. With the right tools in place, Mars can be applied in a wide range of domains. But to truly see its power in action, let's examine a real-world case study: how Mars was used to predict housing prices and outperformed traditional regression models. That's what we're diving into next. Predicting housing prices is a classic challenge in data science. Property values don't follow a simple linear pattern. Location, square footage, proximity to schools, market trends, and dozens of other factors all interact in complex ways. Traditional linear regression struggles with this kind of problem because it assumes a fixed relationship between predictors and price. But housing markets are nonlinear, full of sudden shifts and interactions that require a more adaptive modeling approach. That's exactly why Mars was chosen for this case study. The objective was straightforward: Build a model that accurately predicts housing prices based on key features like square footage, number of bedrooms, lot size, location, and neighborhood characteristics. A dataset of 10,000 housing transactions was used, containing 15 predictor variables. MARS was implemented using a two-phase process. The forward pass started with an intercept-only model and incrementally added 50 basis functions, identifying key points where relationships between variables changed. This phase ensured the model captured important nonlinear trends, such as how price increases for square footage might slow down at higher values, or how neighborhood effects might vary based on lot size. Once the forward pass was complete, the backward pass pruned the model down to 20 basis functions, removing those that didn't significantly improve predictive accuracy. This helped prevent overfitting, ensuring that the final model could generalize well to new housing data. The results were clear. MARS outperformed traditional linear regression. The root mean square error, RMSE, for MARS was 15,000 USD, significantly lower than the 25,000 USD RMSE produced by the linear model. The analysis also revealed that square footage and proximity to schools were the strongest predictors of price, while certain neighborhood effects only became significant above specific lot sizes, a pattern that linear regression completely failed to capture. By allowing the data to dictate where relationships changed, MARS created a more flexible, more accurate predictive model. It was able to detect interactions that standard regression models missed, proving once again that real-world data isn't always linear, and neither should our models be. But as powerful as MARS is today, its future is even more exciting. With advances in machine learning and computational efficiency, MARS is evolving beyond its original form. What happens when we combine MARS with deep learning or ensemble methods? How can we make it scale even better for massive datasets? That's what we're exploring next, the future of MARS. MARS has already proven itself as a powerful tool for modeling complex nonlinear relationships, but its evolution is far from over. As data science advances, MARS is being refined, optimized, and even integrated with other machine learning techniques to create even more powerful predictive models. The future of MARS isn't just about making it better, it's about making it faster, more scalable, and more intelligent. One of the biggest areas of improvement is computational efficiency. MARS, in its current form, can be computationally expensive, especially in high-dimensional datasets where many potential basis functions need to be tested and pruned. Ongoing research is focused on optimizing the underlying algorithms, reducing time complexity from ON2 to ON log n in larger datasets. Parallel processing techniques are also being explored, leveraging GPU acceleration and distributed computing to speed up both the forward and backward passes, making MARS more scalable for big data applications. Another exciting direction is the integration of MARS with machine learning models. While MARS is highly flexible, it still has limitations in capturing highly complex feature interactions that deep learning models handle well. Hybrid models that combine MARS with neural networks, random forest, or ensemble methods are being developed to get the best of both worlds. MARS provides interpretability and structure, while deep learning and ensemble techniques enhance predictive power. This approach is particularly promising in applications like healthcare and finance, where understanding the why behind predictions is just as important as accuracy. Automated feature selection is another game changer. Currently, MARS still requires some manual tuning to optimize the number of basis functions and interaction depth. New advancements in auto-tuning techniques are making MARS even more efficient by dynamically selecting the most important predictors and automatically adjusting complexity levels based on cross-validation performance. MARS is also evolving into a more accessible, user-friendly tool. Improvements in software implementations, such as better visualization tools, interactive model exploration, and integration with AI-driven analytics platforms, are making Mars more accessible to business analysts and decision makers, not just data scientists. As we push forward into an era of ever-growing data complexity, Mars is poised to remain a key player in predictive modeling. Whether it's through faster computation, hybrid modeling, or automated optimization, the future of Mars is all about making it smarter, more efficient, and more powerful than ever before. But before we close, let's take a step back and summarize everything we've explored. What are the key takeaways from Mars? Let's wrap things up. Mars isn't just another regression technique. It's a powerful adaptive modeling approach that bridges the gap between simplicity and flexibility, capturing complex relationships in data that traditional models often miss. Over the course of this journey, we've explored how Mars builds itself dynamically, how it automatically detects nonlinear patterns and interactions, and how it balances predictive power with interpretability. At its core, Mars thrives on its two-phase process. The forward pass aggressively adds basis functions, searching for every possible pattern in the data. The backward pass then refines the model, pruning unnecessary terms to prevent overfitting and ensure generalization to new data. This combination allows Mars to be highly flexible, yet still manageable in terms of interpretability. Mars outshines traditional regression models when dealing with high-dimensional, nonlinear data, making it especially useful in fields like finance, healthcare, and marketing, whether predicting credit risk, patient outcomes, or customer purchasing behavior. Mars has proven to be a game changer, uncovering insights that standard models simply cannot. But it's not without its challenges. Computational complexity, sensitivity to data quality, and the need for careful pruning mean that Mars requires thoughtful implementation. However, advancements in parallel computing, hybrid modeling, and automated optimization are shaping the future of Mars, making it faster, more scalable, and even more powerful. As data science continues to evolve, Mars remains an essential tool for those looking to move beyond linear assumptions and truly understand the hidden structures within their data. Whether used as a standalone technique or combined with other machine learning models, Mars proves that modeling isn't just about fitting equations. It's about letting the data tell its own story.